right, so today I get to talk about two of my favorite topics in the whole world, supernovae and binary stars in the same talk, which is brilliant. And I'm going to give you an overview, but I'll also give you some of the spicy plots towards the end, some actual science for those of you who like light curves and really ugly data. But also, this is a great opportunity for me to give you a taste of the field as a whole that this fits in. Because supernovae and superluminous supernovae fit in that whole revolution of transient astronomy that we have been going through in the past 10 years or so. So when I say transient astronomy, I mean the study of things that change in the night sky on the scale of days, months, or even a human lifetime. That is very short compared to the scale of what happens in the universe. And transient astronomy, the way you used to do it is that you look at the night sky and wait for something to change. Maybe a new star would appear and you'd be like, aha, this is interesting, I wonder what that is. And then you look a little closer and it turns out it will be one of the best studied supernovae in the whole of modern astronomy. That's how 1987A was discovered decades and decades ago. It was discovered independently by someone in Chile and someone in New Zealand, so it's very close to home. It's in the Large Magellanic Cloud. Some of you will recognize 30 Doradus in this image. And this was taken a few months, a few years actually, after the fact. Now, the problem with things like 1987A is if you just wait for things to happen, you're not going to see supernovae very, very often. And if you want to understand the kind of stars that give you explosions like these, you need a large sample. You need more data. So how do you get more data? Well, the first problem you're going to be facing is that the sky is, in fact, and this is true, really, really big. And so you're going to either be very lucky or maybe create your own luck. And in order to create your own luck, you're going to make telescopes and instruments dedicated to surveying the night sky. So in this image, I have summarized some of the first and latest generation of telescopes, fields of view that survey the night sky currently, or that used to survey the night sky. PTF has been retired, for example. So just for your information, all of these fields of view are to scale with respect to each other and with respect to Andromeda and the Moon. They are not to scale with respect to the sky in the background, obviously, unfortunately. And when we look at things like SDSS, the Sloan Digital Sky Survey that had its first light in 2000, so that was 2 decades ago now, it was revolutionary at the time. It was absolutely gigantic, but it is dwarfed by some of the modern facilities we have, like the Zwicky Transient Factory or Assassin, which is, it doesn't fit on the picture. This is just a quarter of it. There are 20 telescopes. It's absolutely massive. It just doesn't fit. And with all of these new facilities, we are finding a lot of new transients every day, and faster than ever before, actually. So this is a little plot I compiled myself by looking it up on the interwebs. The number of transients found since July 2015. It was just a convenient date. So you can see that since that date, we have found about 75,000 new transients. So anything new in the night sky, that's the black line. And in blue, we have the number of new transients per day on average. So we were around 25 years ago, we're around 80 now, and you see it's been increasing. Now, there's a few bumps. For example, IPTF, the Intermediate Palma Transit Factory, closed in 2017, so that caused a bit of a dip. And then it reopened as ZTF, a brand new facility, increasing the number of new transients found per day massively. And then in 2020, you know, not so great. But we've recovered since then. We're doing much better, right? And so with all of these new transients we found, that can be anything, okay? Supernovae are definitely my favorite, but it's tidal disruption events, novae, fast blue transients. I'm not going to describe what these are, but you can take a picture and then ask me at the end, why not? Some of these are just not, not particularly relevant to the plot I had before. Fast radio bursts are actually radio bursts, and so you can't really observe them with optical telescopes, but they count as transients technically, and transients is really anything that comes and goes unexpectedly in the night sky. Now, of course, supernovae are one of them, and they're my favorite by far, not only because they're pretty, and yes, they are very pretty. If you've ever been to one of my talks, you have most certainly seen this image, because this is the best picture we have of the Crab Nebula. And this is a real image. It looks fake. It looks like CGI because you can see the structure here of the Pinwheel Nebula with the pulsar in the middle. You can just about make out the jet. This is X-ray images, and this is real. It was taken with Chandra for one of its anniversaries. So supernovae are fantastic, but they come in different flavors, really. And if you want to split them, there's a number of ways you could do it. The way I'm going to do it right now is evolutionary speaking. So what kinds of stars do they come from? There are two main kinds of stars that supernovae come from, the low-mass stars and the high-mass stars. The low-mass stars are the ones that are born with less than 8 times the mass of the sun. And those stars, in order to become a supernova, they need a bit of help. They need to do a few things. First of all, they need to die, which takes a while. And when they die, they turn into white dwarfs, which is just the dead core of the star that's not doing very much. But the dead core of that star has a very interesting property. If it reaches 1.4 times the mass of the sun, it becomes unstable and it explodes. And that's what's going to create that supernova, that type 1a or thermonuclear supernova. In order to reach that mass, though, it needs a little bit of help. Either a companion is getting a little too close and the white dwarf starts hoovering up the outside of that star, or maybe 2 white dwarfs just get to merge or collide to reach that mass. Now, here's the thing. The cool ones come from the high-mass stars. These are my favorite supernovae, and for many, many reasons, including the fact that they are basically the violent death of a star that is 100,000, a million times the luminosity of the sun, which is incredible. Now, in order to understand how you go from a very high-mass star to a deadly explosion, you need to understand what keeps our star together. And in order to do that, we're going to use some visual aids. The life of a star is guided by the everlasting battle between fusion, and gravity. All the nerds will love this one. Between fusion and gravity. Now we need a little bit of a more helpful diagram. So we've got this. Imagine this is a star. We've got gravity pushing everything in because it's very, very heavy. And we've got fusion in the center, which creates a lot of pressure, which pushes everything out. And that balances perfectly. In technical terms, it's called hydrostatic equilibrium, if you want to Google it. Now, for that fusion to work, we need fuel. Fusion is a nuclear reaction. You need nuclei. So which nuclei are we going to use? Well, it depends. You're going to start with hydrogen, first of all. That's the most common element in the universe. It's also the best to burn. And so when our star begins its life, it's going to burn hydrogen in its core. The problem is that eventually it's going to run out of hydrogen, and it's going to have to go to the next best thing. That's going to be helium. Eventually it's going to run out, it's going to go to carbon, and it's going to go all the way up to iron. And then things are going to get a little freaky, because iron is not a good fuel. It cannot be used as fuel, and here is why. So this graph looks a little intimidating, but I promise you I will walk you through it. This is the average binding energy per nucleon. Ignore that. Basically, it means it can tell you how much energy is released in a nuclear reaction, whether it is fusion, so put 2 things together and make something new, or fission, split the atom. If you start at the very high mass end, so uranium over here, in order to make energy, basically you want to go up that curve, whichever way you go, actually. If you want to go up, you go from hydrogen to helium, for example, and you see you go up a lot, so you release a lot of energy. Or you can go from uranium to, I don't know what the byproduct is, but somewhere up there, and you release a lot of energy. Now, for our stars, we start here, we go there. That's brilliant. That's going to power 90% of the life of our star because there is such a difference between the hydrogen and the helium. Now, if you look between hydrogen and carbon, that's tiny, so that's not going to work very well. So you're going to run out of your helium very quickly, and then you're going to go from carbon to oxygen, you're going to run out even faster, and it's going to get worse and worse and worse until you get to iron. And iron is at the tippy top of the curve, which means that you're going to go down whichever way you go, which means you can't release energy, which means that fusion loses and gravity wins. And if gravity wins, the core collapses. In about 1/4 of a second, the equivalent of 1 to 1.5 times the mass of the sun are going to condense into an object about 10 kilometers across. The pressure is going to be so high that the protons and the electrons are going to be forced together to make neutrons, and you're going to get what we call a neutron star. Now, that neutron star is so dense that if only one of your red blood cells was made of neutron star material, it would weigh about as much as Donald Trump. And you've got to admit, that's pretty dense. I had to do it. And then you get this, beautiful. It takes about 300 years and 4 space telescopes, but who cares? And you can even see a neutron star in the middle, which is beautiful. This is Cassiopeia A, and it is a core collapse supernova, one of my favorites. Now, the good thing with supernovae is that they release a lot of energy. And that's fantastic because that's why we can see them. Now, what's really crazy about them is that only 1% of 1% is actually their light. Most of their energy comes out in neutrinos. If you know where they are, brilliant. If you don't, just ignore this part. If you don't know what this unit is, I love to put it in there because it's a special kind of unit. It's astronomer units. We like to use our very own things. It's not the international system. We just make our own units. This is in centimeters, grams, something, seconds. It's horrible. It's 10 to the minus 7 joules. So you need more orders of magnitude than you would with joules, but it's a supernova, so it's really energetic already, so you're just making the numbers bigger for no reason. Anyways, it makes no sense. I love it. So 1% of that is going to go into the kinetic energy, which is basically the energy that goes into yeeting all of the material from the star out into interstellar space. I know, I love it. And that ejector is going to be accelerated to speeds of about 10,000 kilometers per second. Now you might think, well, that's a little bit fast. She must have just taken the highest number that she could possibly get just to put it in the talk. But no, 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 no. I have worked with supernovae that had areas of that ejector that went at 30,000 kilometers per second. This number is an average supernova on a Tuesday afternoon. This is not impressive whatsoever, I can assure you. Now, as far as the light is concerned, it is very impressive. You can see them from very large distances. Most of the supernovae that we see are from outside of the galaxy. We haven't seen one in the galaxy in quite a while, actually. And they can often outshine their own galaxy, which is pretty cool. But that's not the only cool things about supernovae. They're not just violent and shiny. They are also all very different. And that's because they come from very different stars. Now, you can split your supernovae into 2 types, type 1 and type 2. Type 1 meaning that they show no hydrogen, and type 2 meaning that they do show hydrogen. And that tells you about the star that exploded. So the star that had, the supernova that had hydrogen, obviously the star had some hydrogen left. And that's pretty normal for a star. By the time it dies, the core is devoid of hydrogen and everything. But the rest of the envelope is fine. It's still there. It can't reach this part of the star. So it's pretty standard, and most core collapse supernovae will show hydrogen. But sometimes they don't. And that's because sometimes the envelope of the star gets shedded by stellar winds, or because there was a friend that came a little too close and started eating up the hydrogen, and sometimes it takes the helium with it too. Right, so that's really important for later in the talk. You do not need to pay any attention to the 2b, 1b, 1c. This is just leftover from a lecture I gave a little while ago. Just remember the 1 and the 2, and I will remind you anyways. Now, if you go back to this beautiful plot, you may have guessed that we have seen quite a few supernovae of all different types in the past few decades. But what's really cool is that we've also seen supernovae that are rarer and brighter than ever before. And by that I mean the superluminous supernovae. Segue into the topic of my talk. Brilliant. Love it. Now, superluminous supernovae have this exact definition if you're a magnitude type of person. Their absolute magnitude has to be minus 19.8 or lower. Now, if you don't know what magnitudes are, welcome to the world of magnitudes, where up and down is up, because minus is big in this world. So we're going up this way, people. We're going up this way. And core collapse supernovae over here, minus 16, minus 18.5, that's, bright, but not bright enough. Superluminous supernovae are over there in the blue and in the red. The blues are types 1, the type 2s are the red. We're going to ignore those, so just so you know. Now, ignore the green bit. There. These ones are too bright, and these ones you ignore. So why are these too bright? They're not just bright, they're too bright, because this line here is very conveniently showing us the maximum energy that can be given by a type of supernova, whether it's thermonucleus of the type 1 or the core collapse supernovae. Why is there a maximum energy that a core collapse supernova can give you? Well, that's very simple. The more massive the star that collapses, the bigger the shock, the more energy. The problem is that if your star is too big, it's not going to make a neutron star, it's going to make a black hole, which is going to suck everything back up. You get no supernova. So there's going to be a point that you reach where you just don't explode anymore. And that's why you can't make these superluminous supernovae with the traditional core collapse mechanism. So you need something else. And that something else is often the magnetar. That is the best scenario that we have at the moment, where basically, because we don't have enough energy, we need an extra boost. So we're going to put our neutron star on steroids and give it a massive magnetic field, make it rotate every 2 to 3 milliseconds, and that's going to help the ejector. Why does that help? Because this magnetic field is very, very powerful, and the ejector is very, very hot. Right? That's stellar material that's been exploded by the supernova. Because it's so hot, it's magnetically charged, so it can actually talk, it can actually connect to this magnetic field of the neutron star. We say it is coupled, and it can steal energy from the magnetar, and it can be brighter than it normally would be. But sometimes the magnetar is not enough. And this is where we go into the actual science of it all. 2017 GCI, this is a bit of a phone number, but we're going to get used to it. It's a type 1 superluminous supernova, type 1, no hydrogen, remember? And it has a bumpy tail. Now, the bumpy tail is the thing that caught my attention, you see, because that's very interesting. This is what it looks like. This is what our bumpy tail looks like. This is the actual data from the paper. So we've got the data in dark blue, and we've got the magnetar model in orange. And you can see the magnetar model does a very good job at reproducing the overall shape of those data points. That's nice. Ignore this, ignore this. But there is stuff going on that can't be explained by the magnetar. So what's happening here? What's very likely is that you've got clouds of gas and dust surrounding the supernova. And so what happens is that you've got your supernova going off, right? And when you're right here, it fits the magnetar model nicely, so it's just doing its thing. It's all good. But then it expands, and it reaches a cloud, and you get a bump. Because the shock between... Oh! I knocked out the batteries out of the thing. Because the shock, as I was saying, between... That was a very good representation of the shock, actually. So the shock between the supernova and the gas and the dust is going to create... energy is going to, well, it's going to release energy, rather, into light. And so that extra light is something that you can see in the light curve. And then later on, the ejector expands further, another shell of gas and dust, another bump, another day, another shell, another bump, right? Okay, you get the gist. Now, the problem is, where does that come from? How do you make the shells of gas and dust? And if I had to bet on anything, it would be on the binary hypothesis. And the reason is that, well, there are two reasons, actually. First of all, binary stars are ubiquitous. Binary stars is when you have two stars that rotate around each other and they spend their lives together, and it's a lovely dance, but things can happen. Now, these are very common in massive stars. This is an ugly plot once again, but I promise I will explain. So these people, in 2017, came out with a massive survey of loads of star systems across loads of different masses and counted how many binaries there were. And it turns out that at the high mass end, so above like 8 solar masses, most of the systems are very close to a binary fraction of 1. So this is like all of the system, 100% are in binary systems. A bit below is like, well, not all of them. And above means that some of them are in binary systems, and some of them are in ternary systems and quadruple systems, et cetera, et cetera, et cetera. So binary interactions are ubiquitous in massive stars, but also they're very messy, as we have seen before. Now, in the case before, it was a white dwarf and another star, but the fact remains that they are very messy. You can transfer mass from one star to another. You can get a common envelope between the two. You can get mass ejection. And so because of that, my best guess for these bumps when I first saw them was that there were binary interactions just before the death of the supernova. And why do I say just before? Because those bumps were a few hundred days after the maximum light, after the peak of the light curve, right? But for that to be the case, you would need to expel that material from the system a few decades before the star exploded, which is nothing on the scale of the universe. So it has to happen just before it dies. So how are we going to figure out whether binary stars can do this? Well, we're going to use models that were made partially in Auckland. MPhys is internationally renowned. I can actually say that because literally everyone uses it, so that's great. My boss is the leader of this binary population code with some colleagues in the UK, and my contribution is HOKI, which I will talk very briefly just to show off later on in the talk. So what's MPhys? As you can tell, I have nicked some of these slides from actual conference talk slides, so if they look intimidating, don't worry, you don't need to look that stuff up, I will explain. So what's MPhys is basically a mini universe in a box in a computer. What you do is that you take all of the stuff you know about stellar evolution, about how stars are born, about how they live their life, about how they interact with each other, and you put all of these pieces together, and then you evolve it forward in time and see what it looks like, and record that every step of the way so that you can compare it to what we see in the night sky and see if what we understand actually matches reality. So how do you make a mini universe in a box? Well, first of all, you have to make your stars, and you have to make them right, because you can't just make a random number of stars like the sun and then, I don't know, 10 stars that are half the mass of the sun, and then, you can't do that. The universe has there is method to this madness, okay? If you have one star that is the mass of the sun in your simulation, you will need between 20 and 100 stars that are half the mass of the sun. But you'll only be able to have 0.007 stars that are 10 times the mass of the sun or above. And these are the stars that give us supernovae. So you need quite a lot of stars in your mini universe in order to have stars that can explode as supernovae. And now you might think, hold on a minute, that number is tiny. Why do we bother? Why even care? Why do they matter? Well, they matter the most, actually. Because these stars are very powerful. These supernovae are what release the stuff that you are made of. And also they evolve very quickly, in about 3 million years, which is quick on the scale of the universe. These stars, they have a lifetime of a few trillion years, which you may know is longer than the age of the universe, which is a bit inconvenient. It means that all of the gas in those stars is locked away and we can't do anything about it. So they're a little bit useless. So you need all of these stars to have a realistic universe. Now, once you have these, you need to make sure they're made of the right thing. So let me introduce you to the periodic table of elements by astronomers, which is hydrogen, helium, and metals. It's a classic, we love it. You can't have an astronomy talk without that. It's very convenient, I love it. Now, why do we do this? Because 75% of the universe is this one, 25% is this one, and some percentage taken away from either one is everything else. Now, the everything else is actually very important as it so happens, because it tells you about the stellar winds, it tells you about mass ejection, it tells you about how the star will expand, evolve, all of that stuff. So you need to get that right, or at least you need to have a few options. In our simulations, we have 13 different options that people can choose from, or that I can choose from, to try and match what we see in the universe. And the other thing we need to get right is the binaries. I mean, we're called the Binary Population and Spectral Synthesis Code. We need to get that right, at least. So what we're using is actually the paper that had the ugly plot earlier that I showed you. It's an ugly plot, but a very good paper, I swear. And it tells you about the periods, so how quickly the stars rotate around each other, and the mass ratios, so how big they are with respect to each other, of loads and loads of different stars across different mass ranges. And because we can put all of that in our simulation, we can get the binary population right. Now, this plot is really cool, a bit irrelevant, but it's beautiful, and I really wanted to show it. This is beta Lyrae, it's a binary, and this is a real GIF taken over 13 days, and you can see the reason that it's a little squished like that is because these stars are contact binaries. One of them has expanded so much that it is actually touching the other one like a droplet, and they're going around like this, and you can see it. Oh, this is beautiful. Anyways, I digress. Yes, so we have all of this, then we evolve it forward, then we do something with the spectra, which we're not going to need today, so we don't need to talk about it, and we have then HOKI. Why do we have this? Mostly because astronomy is complicated, and I like to make my life easier. So I have automated all of the really boring chore tasks in my job, and I've put it in a package. Now we can skim over this, because realistically, that's more the kind of ad I have in conferences to say, use my code, please, but you don't really need to know about this. But the reason that Hoki is really cool is that we can search through 250,000 stellar models really, really, really quickly in order to find, potentially, the progenitor system of our superluminous supernova that had the shells of stuff around it. Now, how do we do this? Well, we're going to take everything that we know about that system, and we're going to put it together, and then we're going to go look for stars that do that in MPhys. So the first thing we know is the metallicity. It's less than half solar, it's in the paper, it's in the galaxy, we know that it's brilliant. In the galaxy that supernova came from, not this galaxy. The mass of the system is above 10 solar masses. That's not really a search criteria, to be honest, is to make the computation easy. The remnant mass, so that's the thing that's left after the superluminous supernova, that has to be less than 2.43 times the mass of the sun. Why? Because we need a neutron star. We need a magnetar, therefore we need to make sure this is a neutron star, not a black hole. And this is the current best estimate for the maximum mass of a neutron star. Then the ejecta mass is between 8 and 13 solar masses, it's in the paper, and the very interesting bit is the hydrogen content. And the hydrogen content is quite delicate, because we need to make sure that it's a type 1 at the end of its life, so it's got no hydrogen left, so the mass needs to be less than 0.001 times the mass of the sun. X is just the hydrogen fraction, so 1 means that your material is fully hydrogen, 0 means that it's no hydrogen at all, but it needs to be very, very low. And why is this really complicated? Because these things have hydrogen in them. And so, because that stuff was made like decades before the star actually exploded, you need to keep hydrogen in the star until it dies. You need to walk that very fine line that you keep the hydrogen for long enough, but then lose it at the right time so that you can have both observations simultaneously correct. I didn't think I was going to find anything, but I did. I found 2 matches, which is brilliant. And this is what we can do with MPhys. When you find those matches, those stars at the end of their lives, you can then rewind the tape and look at what they went through throughout their lives. And here is the life story of that star as far as we know it. So it was born as a 30 solar mass star. 30 solar mass star progenitor, 30 times the mass of the sun. It had a friend, which was either a 12 solar mass star or a 25 solar mass black hole. Now we're going to ignore this, because this is very, very, very rare in the universe. This is much more likely, like 110 times more likely to be precise. So this is why I made the plot with the 12 solar mass star. But realistically, this one's not going to do anything during the lifetime of this one, so it doesn't actually matter. So what's our star going to do? Well, eventually it's going to run out of hydrogen, so it's going to go through 90% of its life doing nothing, pretty much. But then it gets interesting, because when it runs out of hydrogen in the core, it burns hydrogen in the shell, and it expands massively. It expands so much, in fact, like hundreds of solar radii, hundreds of times the radius of the sun, that you're going to basically gobble the other star and share an envelope for a little while. When I say a little while, I mean nearly 4,000 years. And that's going to be very effective at removing material from our 30 solar mass star. You're going to lose 12 solar mass worth of material and 8 solar masses worth of hydrogen. So we're quite a bit of the way through. This is very encouraging. The next thing is mass transfer. So by that time, we've lost a lot of hydrogen, so the star is getting a little bit smaller. It can't keep being that big, but it's still a little too big. It's still a little too close to its friend, and it keeps losing mass, but just in a nice stream going to its friend. It's not gobbling up the whole thing. That's going to last a little bit longer, but not be quite as effective at losing hydrogen. And that's very inconvenient for me, you see, because I was hoping that my binary interactions were going to be good enough to do the job, and they were not. So this is, it's boring, but I love it. It's boring because there's a lot going on, and it's not particularly pretty, but I swear it's going to pay off. So this is the final few thousands of years of the life of our star. So all of the stuff I've ignored is the 90% of the lifetime that does nothing. And here is where it gets interesting. So this is the radius in red, the radius of the star that shoots up massively when it runs out of hydrogen in the core. And that's where you start immediately the common envelope, which is, and see it's color-coded. Ha, orange, orange. I thought about this. Then common envelope stops. The radius, poof, comes down, mass transfer. Now, what you need to keep what I needed to keep an eye on was my hydrogen mass fraction, because I wanted to go there, but it's still there. It's only halfway down, which is a problem. The mass of the hydrogen in blue is also not at 0, which is another big problem. And so that's going to keep going down, obviously, because it's burning, it's still burning hydrogen and stuff. But you're going to need something else to get to the right point at the end. And what that other thing is strong winds in blue. What are those strong winds? Well, when the star is getting very, very close to death and is burning helium in a shell, it's going to get really bright. And it's going to get so bright, in fact, that the outside of the star is going to just go out into space, be like, oh no, can't do this anymore, going on strike. Radiation pressure is one of the dominating effects of very massive stars, especially towards the late stages of their life. Basically, light pushes things away, and when they get this bright, they lose a lot of mass, and that's what's going to get rid of those final bits of hydrogen a few thousand years before the death of our star. And then it dies, it does its thing. Kaboom. No kaboom. No penguin. No one gets that joke? Okay, that's fine. They can't all land, So why is this cool? Why is this cool? Because, well, binary interactions are great. The problem is that's not at all what I promised you. That's not at all what I expected. I told you when I started that I expected binary interactions of these things to happen just before the death of the star, and that is not what happened. Why is that really interesting? Because they are still necessary. When I saw this, so stellar winds, FYI, they can happen in single stars, in stars that live their lives on their own. So I thought, damn it. Does that mean that a single star can just do that as well? Turns out they can't. If you look at the single star models, they're either going to lose their hydrogen really early in their life, and then they don't have the shells that can do the bumpy tail, or they're going to not lose the hydrogen enough, and you don't get a type 1 supernova. So you need those early mass transfers in common envelopes in order to explain these really weird supernovae with really weird observations. And so that's super exciting. Oh, that's another conference. Ignore the wording, it's boring. So that's the reason that it's really exciting for me, is because this simulation, BPAS, is everything that we think we know. And the more observations we can recreate and we can match, the more we realize, actually, we do understand this. Now, there's plenty that we don't understand, but it does seem that there is plenty that we do understand. And that's very exciting for the future, because that's what I'm going to use to try and understand kilonovae observations, so that's neutron star mergers, and loads of other type of crazy supernovae that we're going to observe in the next 10 years. So I'm going to leave you with some random thoughts about hokey, transient astronomy, binary interactions, and everything. And I'm going to take your questions about whatever you want. Thank you very much.
Well, that was really fascinating and entertaining as well. So, questions from the audience?
Is hokey an anagram for anything?
No, it's a fish. No, so we're not doing acronyms or anagrams. Astronomy loves acronyms. We love stupid acronyms as well. So we thought we'd do things a little different. Jan Eldridge, who is the leader of the astrophysics group at Auckland, like specifically stellar astrophysics, she's kind of going for a New Zealand theme for our code. So hokey is the fish, we're fishing through the data, all that kind of stuff. We've got a student who wrote a code called Riro Riro for the bird that can be heard but not seen, because it's a code about gravitational waves, modeling gravitational waves, so you can't see those, but you can hear the chirp. And we've got Taka here, which is a code for the kicks of supernovae. And I don't really know why he picked Taka here, can't remember. Anyways, so we're going for New Zealand animals for our codes to kind of like, home pride, that kind of stuff.
Who wrote BPass? Who is the author of this?
So, it's complicated questions. So BPass is based on the stars code, which is a 1970-something code from Cambridge, which is impossible to read because it's written in Fortran. A lot of BPass is also written in Fortran, also impossible to read, but at least Jan wrote it, so she understands it, which is great. Another author is Elizabeth Stanway in Warwick, so she contributed less of the code base. She's more of an observer, but she helped with some of the comments, which is brilliant, and some of the documentation. So it is a complicated history, and some of the basis of that code and the actual evolution of the star, what's going on inside the star, because we have the details of the whole stellar interior and everything. You can see it in text files, I guess. That's from the 1970s, because a lot of that kind of physics hasn't really changed that much, but what has changed is the computational capabilities that we have, so we can keep adding more and more physics because we just have more CPUs and better CPUs. Yes?
The orange envelope with the... that looks like a hokey.
Oh yeah, that's brilliant, I love it. Fish.
A question from the internet. With BPass modelling, is most of the compute done on New Zealand computers, or is it computed overseas?
Aha, very good question. I don't know about the previous, some of the early models would have been overseas, but actually Jan uses NESI, which is a cluster of computers in Auckland University, or associated with Auckland University. I don't know if they're an independent thing, but it is a lot of NESI time. And all of the models that I use nowadays, they're the updated models, so they are, home models.
Does BPass actually simulate the actual supernova, or does it?
It does not. It does not. That's a very good question. So the actual supernova is not modeled by BPass. BPass, what it does is that it assumes 3 different versions of a supernova. A standard one, which is 10 to the 51 ergs, which is, by the way, it's called a FO, which is very villainy. I don't know why we call it that, but that's the name of the unit. 10 to the 52 as well for the very energetic ones, which is what I used for the luminous supernovae, because 10 to the 51 is what you would expect from a core collapse. This is 10 times more energetic, so you go for the high mass one. And there is a version for 10 times less energy as well. And all it does is kind of it's not really back of the envelope, but it's a zero sum of how much mass is left in the neutron star or the black hole, how much mass was there in the star when it died, and that is how much mass is ejected. Supernova simulations are very difficult, and people are still trying to explode supernovae, to be honest. They're still trying to figure out all of the knobs that you need to turn in which position exactly to make it explode properly. And one of the things that can make a big difference is whether you use 2D or 3D. So for example, there are loads of supernova models that do not explode in 2 dimensions, that do explode in 3 dimensions, because magic, I guess. So.
Okay. And another question about supernova. There's a type they call a pair instability supernova. Are they for real? Is that being confirmed with observations?
Yeah, so for everyone else, pair instability supernova is actually another potential candidate for some superluminous supernovae. So a pair instability supernova is from a very, very massive star, something that is so massive that when it gets to a helium, well, it's making helium in the core, so it's burning hydrogen. When it gets to a helium core mass that's 64 times the mass of the sun or something like that, it's in a very weird state where the density is rather low and the temperature is ridiculously high. So randomly, the photons decide, I'm going to turn into an electron-positron pair, which is why pair instability. It's an instability where the photons just, boop, turn into something else. The reason that's a problem is because your photons in this regime is what keeps the star from collapsing, which is a problem. So the star is going to condense very quickly, well, on the scale of the universe, and then it's going to undergo a thermonuclear runaway, and the whole thing's going to get disrupted and exploded. And because the whole thing explodes in this thermonuclear runaway, that's a lot of energy, that's a lot of light. And that's why they are candidates for some superluminous supernovae. To answer your question, we have candidates per instability supernovae. There's a bit of a list, but there is nothing confirmed yet. But there are candidates. And one of the very difficult things with per instability supernovae is realistically, we don't fully understand the physics. There was a recent paper that came out earlier this year talking about the uncertainties on that mechanism, and it can give you stars like of masses, core masses that change by like an order of magnitude. So we are still working through that, because the more massive the star, the rarer it is. Just for a 10 solar mass star, you're looking at a few hundredth a few hundred stars like the sun for one star that's like 10 times the mass of the sun. It gets even lower for the stars that are like 100 times the mass of the sun that you need for per instability supernovae. Because they're so rare, it's very difficult for us to compare our theory to observations. So that's them.
Any more off the internet, Steve?
Yep.
And from the audience?
What happens to the partner of a binary star where one goes supernova?
After the supernova, you mean?
Yes.
Very good question. It depends on how close it is. So if it's nearby enough, the ejector is going to collide with the envelope and is going to make it bloat because it heats it up. And it's kind of like any normal gas. If you heat it up, it just expands. It's going to expand, it's going to lose some material, and then it's going to condense back again. It's also possible with the kick from the supernova that the binary system would be disrupted, so it just loses its friend. But if it's far enough, like the closer it is, the more likely it is that something catastrophic will happen. Either a lot of mass is going to get lost from the companion, or something's going to get kicked out. If you're really far apart, then even a decent kick might not disrupt the orbit that much. So yeah, it depends.
Okay, in that case, thanks very much, Heloise. It was